Alright, this video is to extend some of the topics that we were talking about this past Tuesday. Um, I failed to present a couple other pretty basic ideas, but I'm going to use this video to also recap some of the last things that we were talking about. So just to go over some of the slides that are now available to you. I wanted to revisit the layers of the atmosphere. So we talked about how originally, just like the pressure and density of the air decreases with height, many scientists thought that the temperature should decrease with height. After all, when you climb a mountain, it does get colder, but we did find through sending weather balloons up there and measuring temperatures of the upper atmosphere that there are fluctuations in temperature as you go up in height. In particular, if you look in this picture, you can see one of the clouds that we were talking about. This is a Cumulonimbus Cloud, typical for supercell thunderstorms, where you have this large updraft that builds the cloud upwards, but then it caps and it starts to form the typical anvil shape. But that cap is formed because of the change in temperature that happens above this layer. And so, since this is the layer where all of the action happens, where all of the weather that we know of occurs, we call that the troposphere. Where the temperature stops decreasing is called the tropopause. So you can climb in height for a little bit and the temperature doesn't change very much. And it is at this point the temperature begins to rise, and it is in this region that we refer to that as the stratosphere, strato meaning layer. And this is also where you would find the stratospheric ozone layer that helps to protect us from various forms of radiation, like some more high intensity UV rays, ultraviolet rays. But because the concentration of ozone lies here, that's what's doing the absorption of radiation, catching all that heat generated by the sun's deadlier rays. And that's what warms the air up here. But up above the stratosphere, there's not much ozone, and so what ends up happening is we have another pause, the stratopause, and it's in the mesosphere that we see the lowest temperatures in our atmosphere. This is typically where you start to see meteors begin to form. So these are tiny bits of space debris, usually left behind by a comet, but when there are meteor showers, they typically happen certain times of year. That's because the Earth, as it's going around the sun, passes within the path left behind of debris left behind by a comet, and so all that debris begins to fall, and as it picks up momentum, it hits the upper atmosphere and begins to encounter some friction. So the air molecules, the nitrogen, the oxygen that's in the air, begin to rub up against these little particles, and they start to heat up. And so they begin to burn and give off light as they start to emit more heat, and they start to glow. So we often call these guys shooting stars, but in fact they're nothing close to being stars. They're only tiny little fragments. So it's just a nickname that we've given them. They are just pieces of space rock. When they're located up in the in outer space above the atmosphere, we call them meteoroids. When they fall into the atmosphere, we call them meteors. And then when they hit the ground, they are called meteorites. So interestingly enough, we get the word meteorology from the word meteor. And despite the name, meteorology has nothing to do with the study of those space rocks, but everything to do with the study of the atmosphere. And why those names come together is the fact that meteors are those space rocks that burn up while falling through the atmosphere. So that's where the connection is. So in this course, we're studying the weather and climate of the Earth. So that's what a meteorologist studies. A meteor is a rock that falls through the atmosphere. And so that's the deeper connection between those words. Where you would study meteors would be in astronomy or astrogeology. Now, above the mesosphere, it turns out again we have this other pause, and that's because as we reach the boundary between Earth and space, we have the few molecules that are present up here, the first to experience the intense rays of the sun, and so they get very excited, and by absorbing all that radiation, we would characterize that as higher temperatures. So we see on this chart that after another pause, which we call the mesopause, the temperature skyrockets back in the other direction, and so the temperatures can be way off the charts here, but I gave you guys that little riddle in class that although temperatures can be up to 1,000 degrees or more in that upper portion of the atmosphere measured by some thermometer or other device, a person whose skin was exposed to that environment would instantly freeze. And the answer to that riddle comes from the concept that because of the low density, the body doesn't really feel the heat of just the collisions of a few molecules. It's only that at the ground, where the air is so dense, that our bodies tend to fall to equilibrium or rise to equilibrium depending on the temperature of the environment, the surrounding environment. Now, what you see here are the auroras, sometimes in the north called the northern lights, specifically also in the north the aurora borealis. There's also southern lights, but they are more common in the north. It's definitely on my list of things to do. I'd like to go and visit these one day. You have to go very far north. It is possible that they can occur in this area, but the light pollution around here would not really be ideal for us to see this type of phenomenon, and it would also be low along the horizon, so you'd have to have a good look, a good view of your horizon in the north, and also be somewhere where it's extremely dark. So you're going to want to go up far in the north in the Arctic, ideally, to see this. It reaches a peak around the spring, but it's a really beautiful phenomenon. But behind it is the understanding that what you're seeing is that deadly radiation from the sun, and it's being blocked by one of our sources of protection from that radiation, and that's the Earth's magnetic field. So the radiation which would otherwise fall to the Earth and make it very difficult for living things on the surface to exist, instead get caught in the Earth's magnetic field up at the very, very, very top of our atmosphere, and so it never comes down. But as that radiation hits those sparse oxygen and nitrogen molecules and the various other small amounts of molecules that you can find up there. That energy makes those molecules glow specific colors. So you can see a variety of different colors in the aurora, and each color represents the type of gas that's interacting with it in the upper atmosphere. Sometimes the thermosphere is broken up into two layers, so not only the thermosphere but then also the ionosphere. And an ion is what happens when you charge up a molecule like nitrogen or oxygen. When you make them glow like that, it becomes an ion. And so, or a plasma is another word that we often use. So that's why sometimes they do split that up. I typically only use these four, but sometimes you can also include up here an exosphere or an ionosphere. I'm satisfied with these four layers. I had just mentioned when we were talking about the troposphere that there is what we call a lapse rate, an environmental lapse rate. And as you climb through the troposphere, the temperature goes down, but at a pretty fixed rate. And so this is the rate at which the temperature drops over a given height. It's about 3.5 degrees Fahrenheit per every 1,000 feet. So here at the surface, the temperature is 46 degrees, so it's pretty cool at the surface here. But over the first 1,000 feet, that temperature drops 3.5 degrees. So now we're down to 42.5. We drop another 3.5 degrees after another 1,000 feet, and we get to 39. And what you see is that once we get to about 4,000 feet, the air has now cooled to about 32 degrees, which is the freezing point of water. So any moisture in the air would have to freeze into snow. And so this lapse rate will help us to determine where these ice caps will form along the top of mountains. So, with a base temperature of 46 degrees, it would be easy for us to predict that at 4,000 feet you would find that the area of snow begin to develop towards the top of that mountain peak. The last concept that you'll need to know for next week is just the basic difference between weather and climate. The course is called Weather and Climate. What's the big difference? What I want to highlight is that weather describes the short-term state of the atmosphere. So anything that we can measure within the short term constitutes its weather related. So air temperature, that fluctuates moment by moment. So what today's temperature is not going to be what tonight's temperature is going to be, or tomorrow's temperature. It varies. So since that's a short-term idea, measurement, then that has to do with weather. Air pressure, humidity, the different types of clouds, the different types of precipitation, road visibility, wind direction, wind speed, those are things that change moment by moment, and so those help us to describe the state of the atmosphere in the present or over a short period of time. So you look at the Weather Channel or your local news station and they give you the weather forecast. They don't really run that far. So you get today's weather, tomorrow's weather, and then some sort of extended forecast that can take you maybe a week out or a little bit more, like a 10-day forecast. But beyond 10 days, it starts to become very difficult to make accurate predictions because of these variables right here. They change every moment. So you need to try to predict every one of these variables, and there's also many other things that are not on this list, but they're all interrelated. They all affect each other, and therefore that's what makes forecasting weather in the long term almost impossible, because you'd have to have infinite knowledge of what's the changes happening everywhere, and it's just not possible, at least in the short term for us. But what is climate then? Climate is the long-term patterns and average weather. So weather is short-term, climate is long-term. So when we talk about climate, these are things that you could predict about a given area or the state of the atmosphere over long spans of time. Certain places are deserts. Certain places are tundras that receive very little moisture and are typically always very cold. Taigas are regions that receive quite a bit of moisture but are typically very cold. These are aspects of the environment and the atmosphere that help to describe a region over long periods of time. So a desert isn't a desert for just a week or a month or even a year. It took thousands, if not millions of years to develop into that type of climate. Also, whenever you're told things like the sort of the average forecast high or low of the day, or what the record high or record low of the day is, those are quantities that help us describe climate as well. If I told you that the high today, the average high today was 80 degrees, that doesn't tell you that it's going to be 80 degrees. It could certainly be 90 degrees, it could be 70 degrees, all right? But over a long span of time, typically for as long as people have been recording, keeping track of our area's temperatures, we've been able to develop an average to get an idea of what temperatures we can expect. So you can always look them up no matter what day it is and say, okay, usually around this time it should be about 80 degrees. But depending on today's weather or this week's weather, there are patterns that could set up that change and make us go above the average or below the average. So also it's useful to know what those records are, because even though today's high might only be 80, if the record high is 105, then we know it could have been a lot worse, and that it's possible, even in this time of year, that the record could be, that we could hit temperatures that high or low, depending on what you're interested in. So that's essentially the difference between weather and climate. So meteorology, again, in general, study the atmosphere and all its various phenomena. Goes back to the time of Aristotle being interested in trying to make predictions about the weather. It was obviously very important in many aspects of life, and so the Greek culture at that time very interested in nature. Why the telegraph is such an important milestone here is it allowed information to travel very fast across the country, and for the first time quickly relay meteorological data from one place to another over a short period of time to help us understand what could happen. So for instance, generally our weather moves from west to east. So if there's a storm developing in maybe Washington State, that there's a potential that over the next week that storm could move to our area. So if we're told that ahead of time, then we could prepare for um, that system to come. In the 1920s, research was done regarding understanding what air masses are, and in the 1940s, we learned more about upper airflows, which govern the tracks of storms. Interesting story, goes back to World War II. The Japanese had discovered this fast-moving river of air, which we now call the jet stream. And they had devised an instrument that behaves much like a hot air balloon, but it was set on a timer, so that way they attach some sort of bomb-like device to the balloon. They would make the balloon rise all the way up to where the jet stream was. And what it allowed them to do was send this balloon over to the west coast of the United States, which they did successfully at least once. Otherwise, there would be no way they could send a hot air balloon at that time across the vast Pacific Ocean. And so with the discovery of the jet stream, they were able to send that bomb and set up a timer so that it would drop exactly when they predicted the balloon would arrive, traveling at the speed of the jet stream. So very interesting discovery. And by the 1950s, more technology developed to allow for numeric models and predictions that will later be taken on by the role of very powerful computers. A lot of up to that point, I mean, other than just general observations that could be made, the forecasts that were done numerically, those calculations are very complicated. They involve very high-level types of math, and take quite a long time, even in a collaborative effort to do them. So if once the computers started to develop, then they assigned the computers the job of running those models. Nowadays, we have very, very sophisticated technology to run those models, but even those computers, which can do millions and millions of calculations every second, still require hours to do all the calculations that are involved in making a long-range forecast. That perhaps when they say that at the 6 o'clock news that tonight at 11 we'll have an updated forecast, it's usually because it takes a few hours just to get the new information, because the computer is constantly revising and working on the new data. And then, of course, in the 60s, once the space program began and we started launching things in orbit around the Earth, we quickly discovered that satellites were a great tool to make observations of the atmosphere and all of the weather-related phenomena. So this is a radar image that's showing precipitation over portions of Indiana. So it can tell you where the heaviest rain may fall. and you can watch it over time. We have, depending on the types of satellites that we use, different views. Geostationary satellites are those that remain in the same place over time. And so it takes a very specific orbit to do that. These satellites are very, very high up in the above the ground, roughly 36,000 miles off the ground. We had mentioned in class that 250 miles above our head is the space station. They're moving at 18,000 miles an hour, so they'll circle the Earth once every hour and a half. Now, because the Earth is spinning, every hour and a half that they make their way around, they're now over a different location. So they don't always make the same circle around because the Earth is spinning underneath. So the unique quality of a geostationary satellite is the fact that they're launched to a position where, as they fall around the Earth in orbit, they always remain in the same place. It takes, instead of like the space station taking an hour and a half to go around the Earth, the geostationary satellites take 24 hours to go around the Earth. So since that's the same time as the Earth's rotation, then they make it around and at the same time and stay above the same spot. So you can always, with a geostationary satellite, see the same place around the Earth. Whereas meridian measures, so here we're going either meridian or parallels. They're orbiting the Earth in circles, great circles around the Earth at various latitude and longitudes. And so they're able to see big storms or like hurricanes and mid-latitude cyclones. So this is an example. So this is a satellite image with some overlays of some computer graphics. But here what we're seeing, this typical comma shape, is a mature middle latitude cyclone that we're used to seeing in the United States. And then in the tropics, we have tropical storms like hurricanes and some other various thunderstorms fueled by the warm waters of the Gulf of Mexico here. On a weather map, what can you expect to see? The things that change day by day, minute by minute. Wind speed, wind direction. Fronts are the red and the blue lines, sometimes purple. I'll point them out on the next slide. Pressure, which you'll see either as numbers or lines, which we'll talk more about later. Temperature, and then also moisture. So this is another way you can also represent the lowest or highest areas of pressure. So the L means low, the H means high. Those represent pressures. These are called station models. They show you the direction of the wind, where the wind is coming from. So for example, this guy with the tail flag pointing to the left, that means the wind is coming from the west, so it's heading that way. So imagine that this is the head first, moving that way. So you have winds blowing from the west to the east. This is blowing almost out of the south. This is blowing out of the northwest, and so on. The circles, the dots here, some are filled, some are not filled. They can help you tell cloud cover. So here, where it's dark, it's very cloudy. Here, it's clear skies. There's some other symbols here that could help us understand that there's either thunderstorms or other forms of precipitation. But we have what are called the fronts. These are boundaries between different air masses, and this is the occluded front that is formed when a storm, a cyclone, becomes very well developed later on in its lifespan. So again, this is, if looking at weather, here we have a thunderstorm developing and advancing along what we would say an approaching cold front. So there are some signs here of the types of clouds that you can see, and here you can see where it's raining. There's clear signs here that you should be able to identify later, which help us to indicate that there's a cold front coming in. And this is very typical for a cold front, that you have storms, pretty strong storms that develop along this line. And we also know how much that weather and climate can affect our lives. It affects everything from the clothing that we wear, the where and when we grow our crops, the types of utilities that are in use, from air conditioning to heating in the various seasons that we have to concern ourselves with, how much money we're spending. Our health conditions, because we are very delicate creatures of nature and prefer a very specific range of temperatures, and if it's too hot, that's not healthy for us, and if it's too cold, it's not healthy for us. Luckily we have a lot of ways to get comfortable in whatever season we're talking about, but if we are exposed to the elements, that could definitely affect our health. Certainly violent impacts from in all different seasons, depending on your area, where you're from. We've been pretty lucky in the Northeast here. We do have the occasional hurricane that comes through, certainly severe storms, floods, high winds at times. But there are certainly other places, even in the United States, that experience very, very severe types of weather. The Midwest experience quite a bit of tornadoes. You have the droughts in the West causing all those forest fires. The tropics feeling the brunt of all the hurricanes that pass through in hurricane season. So, and the types of impacts that they, leave behind, from fatalities to the destruction of property. Certainly, economies are impacted from transportation, agriculture, sanitation, and so on. And fog is another example of something that could also impact a wide variety of areas within our life. So this is not a pleasant sight. To some, it might be aesthetically pleasing to see the ice crystals form, glazing over the trees and the poles in the area. But this ice storm back in January of '98 caused a lot of power outages and road closures. So that is certainly an impact that has negative effects on that community. This was after Hurricane Sandy back in October of 2012. So Sandy, as it came up the coast, pushed water and sand very far inland. So this guy is digging his car out, not out of snow, but out of sand that came from the coastline, and it was responsible for destroying homes, businesses, and approximately 10,000 cars in this area just alone in Long Beach, New York. Really cool picture of a lightning flash inside of a tornado. This one went through Joplin, Missouri back in 2011. This particular tornado was responsible for going through a hospital and demolishing an entire neighborhood. So these tornadoes, as much as hurricanes are these large systems, which, when they're very strong, could have winds like tornadoes. Tornadoes themselves, very high winds. They don't last that long, but they can pack a punch wherever they begin to form. So this is the aftermath of the tornado that touched down in Joplin, Missouri. So quite a tragedy there. This was a flood in Nashville, Tennessee. So it caused quite a bit of damage to some historical buildings in the area, and so therefore quite a lot of expense to recover from that event. And that is it for this week. Thanks for watching.